Hello. In this video, we're going to go over the heap data structure and in particular how to implement it. I will draw some pictures explaining the insert and remove operations, and then we'll take a look at the code and I will work through the insert operation, implementing the whole thing, leaving the remove operation and some other ancillary operations for you to complete for your homework assignment. Let's get started by sharing my screen. Where'd that button go? There it is. Okay, I've the heap README file opened right here. And the first thing that I want us to talk about with heaps is getting some motivation for why we care about heaps. And to do that, I'm going to do a quick review of all of the data structures that we've seen so far and some of their runtime operations. That's what this table here is showing us. This data structure column shows the different data structures that we've seen so far, and then each of these columns show the different operations that we have been implementing or working with on those data structures. For a list, we've seen that we can insert or at least append to a list in constant time. There's other insertion operations that take longer, but normally we would just be appending to the end of a list if we're using a list, so that insert takes constant time. Finding things, though, the key thing here is finding information inside of a list takes linear time, because if it's unsorted, we have to search through the entire thing. And that doesn't matter whether we're finding an arbitrary element or finding specifically the smallest element. Similarly, removing things from a list takes linear time. A little bit better was the sorted version of the list, because now we can find things in logarithmic time using the binary search. Similarly, find smallest and find both logarithmic time. The downside of the sorted list, though, is that anytime we insert things, we'll have to resort things, and sorting is an expensive operation. So we developed this binary search tree that gives us sort of the best of both worlds: fast insert and fast searches. In general, the typical average case of the binary search tree was really good, that the insert was logarithmic time and the finding operations logarithmic time. But the problem here was the worst case operations, the worst case runtimes. When we have a tree that's very unbalanced, we get these bad runtimes of back even worse than the original list. It's linear to insert one item, quadratic to insert a lot of items, and then finding things is still linear time. So the AVL tree was our saving grace here. It was super complicated to implement, but using it is really great. We get all of these great runtimes. The logarithmic insert in login for inserting lots of things at once, and then our finding operation and our find smallest operations here, logarithmic time as well. The heap improves on the AVL tree only on the find smallest operation. You can see that the AVL tree here, the find smallest operation, takes logarithmic time, theta of log n, but for the heap, we run in constant time. So the heap is an important data structure for when we really need to know what is the smallest item in a list or a container, when we really need to know that many, many times and get very fast results. The heap is used in many places internal to the operating system, when you really need like fast, low-level performance. This is going to be the last of the major data structures here that we'll be talking about, the heap. But I wanted to just emphasize that the particular version of the heap that we're looking at is not the best possible heap. You'll see here that the insert operation is still taking logarithmic time with the heap. And there's this additional type of heap called the Fibonacci heap that also takes constant time to do the inserts and constant time to find the smallest item in the list. The Fibonacci heap is a very complicated data structure. Implementing the Fibonacci heap is, I would say, about 10 times harder than implementing the AVL tree, and it's typically introduced in graduate level algorithms or data structures courses. The Fibonacci heap here is an optimal data structure. With these runtimes here, it can't be improved. Okay, well, let's see. One last issue before we get started on these items here. The textbook here reference chapters 7.8 to 7.10. Just want to take a quick look at those here. When they're talking about heaps in the textbook, another word that you'll see them use is priority queues. Again, we had this differentiation between an abstract data type, which is the interface. So a priority queue is our abstract data type, and then the heap is our actual data structure, the thing that we're implementing. And the particular type of heap that we're implementing is called a binary heap because it's based on the binary tree. But oftentimes people just leave out the word binary and say the word heap, because if you're talking about heaps, it's always a binary heap. So I will be using heaps to represent binary heaps here as well. And again, this idea of a priority queue is anything where you want to get the minimum or maximum element of a container very, very fast. But they're always implemented with heaps, so people use these terms interchangeably. This is section 7.8 right here. Section 7.10 is where you'll find the reference for the things that I will be explaining here in this video. The high-level ideas of everything in the binary heap here, the pictures, these are all great in the textbook. Their implementation, though, is very different than the implementation that you will be doing in the assignment. So you will probably not find the code that they're using here helpful at all. That our assignment, the binary heap, is going to be based off of our binary tree class using the class inheritance. Their implementation of the binary tree is actually based on a list, and so it's the code's just not going to be useful. If during this video the pictures that I draw or the definitions that I state, if those don't make sense, this is a great reference for that, but this is not a good reference for code. Okay, let's get started talking about what a heap is. I'm going to switch over to a screen here where I can draw, and let's start with a motivating example. And make sure my pen is plugged in. There we go. Okay, let's do some blue. So I'm going to start by just drawing a binary tree, and we'll do a very small and simple binary tree. It will have just 3 elements inside of it, 3, 5, and then 1, 0, 3, like this. We know this is a binary tree because it has 2 children. Each node here has at most 2 children, so that's the definition of a binary tree. We also know that this is not a binary search tree. I'll write that out because it's important. Not binary search tree, because we're not satisfying the binary search tree invariant. Here, the child over here on the left-hand side is greater than our root node up here, so that's what makes it not a binary search tree. In the heap data structure, we no longer use this invariant. The heap does not use the BST invariant. And instead, we're going to introduce a new invariant specific to the heap data structure. Let's move this down out of the way. And that invariant, it goes by many names, but the particular name that we'll use is the heap invariant. And what this invariant says is that all children must be greater than their parents. All the children values must be greater than parents. And it turns out that this is the invariant that's going to give us this really fast search time for the minimum value. To me, when I first saw this invariant, this seemed like totally off the wall. Like, I don't know how somebody came up with this, or yeah. the binary search tree invariant, that sort of made sense to me, that then you could like as you're doing a search, you can prune parts of the tree off and remove things. This heap invariant and the heap operations that we'll be talking about seem totally weird to me, and I don't know how somebody came up with it, but it's really cool. This is one of the things that really made me fall in love with computer science right here, because yeah, it's just so weird, but it turns out to be so effective. So the heap invariant, now that we know what this heap invariant is, let's look at this tree over here and ask, does it satisfy the invariant? And the answer is yes, because over here, the 5 is greater than the 3, and the 103 over here is greater than the 3 as well. Let's draw out a larger tree. Here we have, let's add some nodes here, 7 and 9. So both of these two nodes are bigger than this 5, so we're still satisfying this heap invariant over here. And then let's add 105 and 200, still satisfying this heap invariant over here. And over here, let's go crazy and add 3000 like that. And then the number 8 like this. And so all of these nodes here satisfying the heap invariant. One of the things that you'll notice, I didn't emphasize this when we were looking at this table before, but for the heap, there is no find operation. We can't find generic values inside of the data structure. We can only find the smallest value in the data structure. And if we come back over here and look at this heap that I've drawn, maybe this will start to make sense. That the smallest value will always be up here at the top. But if we're looking for a particular value, then like we can't prune off certain branches of the tree. We really would have to look through every single node. And so I guess we could do that. It would be a linear runtime though, so nobody would do that in the heap. For the heap, we only use it if we only care about the smallest of the items and don't want to find arbitrary items. Okay, that's the first thing that every heap must satisfy, and this is the important condition right here, so this is the condition that actually gets the name. There's another condition called the completeness property. Completeness property. And every binary heap is going to have to satisfy this completeness property, but this is somehow a much more trivial property than this heap invariant up here. And so what this is saying is that a tree is complete if there's many equivalent ways of writing this, but the intuition here is that every row has is all the way filled up. So this row right here, this first row only has something inside of it, and so there's just that 3 right here. Then this row right here has a 5 and a 103. This row right here has all 4 of these things, and then any row that's not filled up, we always fill it from left to right, and it's only one row that is not filled up. So I'll write that out in words. All rows are totally filled except the last, which is filled from left to right. So if I were to take this this tree right here and add a new node like this, let's say I add the number 201 right here. This red branch right here, this satisfies the heap invariant because 201 is bigger than 105. But it does not satisfy this completeness property because we're missing some spots over here. That there should be something here and here. This is not a number 0, it's just a spot that there should be something. And if we had things in these orange spots as well, then we could add something here into this red spot and satisfy the completeness property. But if we don't have things in these orange things in these orange locations, we can't have something in this red spot yet. So this tree right here is an example of a tree that is not a valid binary heap because it does not satisfy the completeness property. Another tree that does not satisfy the completeness property would be the subtree. Something like 3, 5, 9, 7, like this. This is not a valid binary heap because it is not complete. It does satisfy the heap invariant because every child is bigger than its parents. But over here, we're missing, this 5 is missing a sibling right here. And so because there was nothing here, it was not a valid binary heap. If we were to add something right here, say let's add the number 4 right here, that still satisfies as a heap invariant. And now we do satisfy the completeness property. So this would be a valid binary heap. There's more alternative ways of describing what it means for a tree to be complete versus not complete. I gave a very informal one right here and some examples. But again, you can refer to the textbook if you want a more formal definition. For the purposes of our assignment, though, we don't need the formal definition. If you understand these examples, then you'll be good for the assignment. Okay. There's two sort of difficult operations on a heap, the insert and the remove minimum operation. Finding the minimum is really easy. Let me come back up here. Finding the minimum of a heap is really easy. You just take the root node, which will have immediate access to. That's why we get constant time operation for finding the minimum. But the insert and remove will be a little bit more complicated. So insert has a 3-step procedure. That's what we'll go over first here. Insert has a 3-step procedure. In the first step, we need to do find what I'm going to call the next position. And so in order to get an intuition about what I mean by this next tuition, let me draw out that same tree again. Oops. 3, 5, 1, 0, 3, 7, 9, 150, 200, 3,008. Then the next position would be this position right here that we have to fill in order to satisfy the completeness property. So this is going to be, this next here is related to the completeness property. I'll describe how to do that in a minute after we go over what these high-level steps are. So that's the first step. And then step 2 will be to add our value into that position. So if we're inserting some number x, add x into that position. And then the last step here, 3, is what we'll call trickle up. And I'll describe what I mean by trickle up here with an example. So here, this x, let's say we're going to insert the value 4 right here. X equals 4. So we're adding 4 into our next position right here. And the problem with adding 4 is that, so we'll satisfy the completeness if we do this, but we're not going to satisfy the heap invariant anymore. In order to do that, we'll have to switch this or move this 4 to a new location. We're not satisfying the heap invariant again because the 4 is less than the 9, and our invariant said that the children must be greater than their parents. So 4 here must be greater than 9. In the trickle up procedure, what we're going to do is we're going to swap the x value with its parent if the parent is greater. So here, the 4 is less than the 9, so the 9 is greater. So then we will swap the 4 and the 9. And when we do that, the 9 will come down here, and the 4 will come up here. Now this node right here does satisfy the heap invariant, but it's not, this node here, our 4, still does not satisfy the heap invariant. So we'll have to repeat this trickle up procedure recursively on every node from our insert node here, potentially all the way up to the root. And so I'll add that right here, swap x as its parent. If the parent is greater, recursively all the way to the root. And so we've done the swap once. Let's do it another time because the 5 here is greater than the 4. So we'll cross out the 4, put the 5 here, cross out the 5, and put the 4 here. And then we'll check, is the 4 greater than the 3? It is, so we're now satisfying both the completeness property and the heap invariant. So this is the high level idea of these of this insert operation, that we first have to find this position down here. Then we'll actually do the insert into that position. And then we do this trickle up procedure, swapping nodes one at a time until we satisfy the heap invariant. We'll go over in code here how to actually do this insert operation in a little bit. But there's still this, like, I don't know, edge case puzzle-ish thing about how exactly do we find this next position down here. That how do I know, should I be going left or right on each of these branches in order to get to the right spot? There's a very non-obvious procedure for doing this, which I'll go over next. The steps are that you first will calculate the number 1 plus the number of nodes in your tree. So in this case right here, we previously had 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes in our tree. So 1 plus 9 equals 10. Next, we will convert that number into binary. So 10 in binary is equal to 1, 0, 1, 0. That, recall, in binary, this is the 1's place, the 2's place, the 4's place, and the 8th place. And so here, when we add this, another color, I'll stick in orange. We have this one right here. 1 times 8 is 8, plus 0 times 4 is 0, plus 1 times 2 is 0, plus 0 times 1 is 0. Adding those together gives us the 10. And so this is our number in binary. Then the last part of this process is that all of these zeros will be implying that we go left, and all the ones implying that we go right as we descend the tree. So I'll explain what that means in this example over here. Yeah, we'll stick with green. So the very first number here is always going to be a 1. This number is always going to be a 1, so we'll ignore this number. And then we have a 0, 1, 0. So starting here at the root, 0 means that we go left. That's the 0. And then we have 1 next. So 1 means we'll go right here. That's the 1. And then we have a 0 as the last number. So a 0 right here. And so that's how I knew that this position right here was going to be the location that I would need to add my 4 into when I'm inserting 4. And it doesn't matter, again, what I'm inserting, the next position right here is always where I'm going to do that insert. Um, yeah. Okay, that's everything about the insert operation. And so we'll talk about the remove operation here next. Again, the insert operation is something that we'll take a look at in code here in a little bit, and the remove operation is one that you'll have to do yourself. So now, remove. And in particular, we can't remove arbitrary elements because we can't even find arbitrary elements. So we're always removing the minimum value from the tree. So the first um, step, again, it'll be a three-step process for us, is that we're going to find the last element in the tree and delete it. And delete it. So I'll draw our sample tree again, 3, it's a 5 right there, 1, 0, 3, 50, 200, 9, 7, 3008, like so. And now when I'm talking about the last element right here, this is the last position that was previously added. So that's this position right here. In order to do that find operation, in order to find this location, it'll be the same procedure that we did for the insert, except we won't be adding 1. For the insert, we added 1 so that we would get the next position right here. For the remove, we won't add 1, so we get the position right here. So it'll be, again, convert number of nodes into binary. In this case, we have 9 nodes. So in binary, that is going to be, what is it, 1, 0, 0, 1. That this is in the ones place, the twos place, the fours place, and the eights place, like this. So 8 plus 1 is equal to 9. And the zeros imply go left. The ones imply go right. And you ignore the very first element because that's always going to be 1. And so now we have 0, 0, 1. Zeros go left. Zeros go left. 1 is go right. And that will get us to this position right here. Step 2 is we will replace the root with whatever value we deleted down here. So again, it's always the root that we are removing because we're removing the minimum, and the heap property guarantees that the root will be the minimum. So let's cross that out. We're deleting that. Put an 8 right there. And then we have totally deleted this, this child right here. We're maintaining the completeness property because there's nothing to the right over here because we're working with the last node that was added. And so in this case, there's only 1 child left on this last row. So replace the root with the deleted value. And then the last third step is a trickle down procedure now. Trickle down instead of trickle up, where we will be swapping the root value with its smallest child. Swap the root value with the smallest child until um, there's no child smaller. So that we'll be satisfying the heap invariant. The trickling procedures ensure that we're satisfying the heap invariant. So in this example up here, we'll have to swap that 8 and the 5 in the first step. The 7 over here is still smaller than 8, so it is breaking the heap invariant. So we will swap that, put the 7 right there, and then the 8 right here. And now there is no node value that is breaking the heap invariant anywhere, and so we are done. Again, it's a very confusing looking tree. Maybe I'll just rewrite this for us, what the final tree looks like. Nothing changed on this right-hand side. 150, 200, then 7, 9, 8, 3,000, like so. Yeah, again, if there's if these explanations about the removing minimum and inserting didn't make full sense, there's good references in the textbook that go over this at a high level. I'm going to be referring back to these notes here, especially the insert notes when I do my insertion coding. And so let's go ahead and start doing that. Come over to our the README file again, and I'm going to scroll down to the homework section. And so we've got a lot of instructions here for the homework, what we're going to be doing. But this first bullet point, what it's saying is that there is actually no heap branch on the GitHub containers repo. And in order to get the branch that you'll need for this homework assignment, I've uploaded that onto GitLab instead. And the purpose of this, again, is just to emphasize that Git is not tied to GitHub. It is just a protocol and works with a large variety of web pages. I have a little historical note for you down here, but I recommend you read through this in detail. But the takeaway message is that Microsoft used to be very reviled, hated in the open source community, especially in the 90s and early 2000s. And as a strategic move, Microsoft in, what was the year? In 2018, Microsoft purchased GitHub. And the reason they did this was to try to get on better terms with the open source community. And they're using their resources as Microsoft, as this large tech giant, in order to offer GitHub Actions as a free service to any open source developer. And so in order for us to have access to a free continuous integration tool for the purposes of this class, we're using GitHub Actions for all of our test case evaluation. There are many other continuous integration tools, but they all cost money. And so we're taking advantage here of Microsoft's generosity in order to test all of our things on GitHub Actions, even though in this case, we're hosting things on GitLab instead of GitHub. Okay, so let's get into the code here of how to do this. I'm going to start by making sure that I copy that URL of where the heap branch is located. And down here, it's telling us, so we'll add a new remote to our local repo on the Lambda server that points to the GitLab repository. So down here, I'm currently on the Lambda server in my containers repository right here, and I'm in my AVL tree branch at this point. Let's go get remote add. The name of the remote that we add doesn't matter. Upstream is a traditional one, but you probably already have an upstream from your previous assignment. So I'll call this one GitLab, pointing to that particular URL. And that's all we have to do there. Then create and check out a branch in your homework called heap. Heap should be based off the BST branch and not the master or AVL tree branches. So currently I'm on the AVL tree branch. You know that because it's showing that here. Also, if I write get branch, it'll show me on the AVL tree branch. But I need to be off of the BST branch. In this case, actually, I'll use the BST solution branch, get checkout BST underscore solution. And again, I've made that branch available to you on GitHub. So if you want to have your assignment based off of my BST solution, you are welcome to do so. For this assignment, you only need the binary tree class to be working. You don't need the binary search tree class to be working. The binary heap will be inherit from binary tree, but not from binary search tree. Okay, so we're in the BST solution branch. Let's create a new branch here called heap, and then get pull GitLab. Here we go. We get a conflict down here in the BST containers. Oh, that looks like, yeah, I forgot to push a change up to the heap here, or up to GitLab. So I'll try to do that before this video is over. So you don't have to do this step here, but I'll go ahead and fix this merge conflict for us. Vim, what are the files? Containers / bst.pst. Search for where the merge conflict is happening at. And oh yeah, so this one's happening because I'm using the solution. And so there we go. Make sure that I'm taking the right piece of code here so that the code still works. There we go. Yep. So that fixes that. And get status. They both modified this containers BST file right here. And so I apologize. I take back what I said about I was going to fix this. This is something that you'll have to do on your own BST branch to make sure that whatever code that you have is going to be different than the code that's on GitLab, and you'll have to do that merge yourself based on where your code is. And so let's now add that containers bst.py and finish up our merge here. Git commit, just call it merged. Now git status, everything there is clean. Let's run our Python 3 pytest -m pytest like that. Make sure that we have the various test cases here. Scroll up to this output, wherever it is, all the way at the top. There we go. Lots of failed test cases at this point. Actually, it looks like my binary search tree is failing a lot, so maybe this wasn't actually the solutions branch. I just named it that and forgot to pull, but that's okay. We'll be focusing on these heap test cases right here. I normally like to have Vim open on the left-hand side, so I just swapped my windows like this. Let's take a look now at the containers. Let's start with a little ls command for us, see what's inside of there. We've now added this heap.py, get status, and let's open up containers / heap.py there. Inside of here, just like in the previous assignments, there's a handful of these fix me's that you will have to fix and implement. The insert one is the one that we will focus on right now. But again, in order to understand the insert and have some confidence that it is working, we are going to have to also take a look at the init is heap satisfied right there. The is heap satisfied function. Oh, yes, conveniently they're right next to each other. The is heap satisfied, it is only going to be checking the heap property and not the completeness property. So that function will only be checking the heap invariant property right here and not the completeness property down here. Actually checking the completeness property is, I don't know, it's a little non-trivial. It's not too hard. It's much easier than the insert function, but it's much harder than this heap invariant right here. And so I didn't want to make you all have to implement that. The completeness property is also a little bit less important than the heap property because it's really easy to just visually inspect things and check that it is working, or check that it's being satisfied. If this were a library that other people were depending on, I would definitely want to have all the possible invariants being checked and enforced. But in this case, just for the purposes of the homework assignment, to make it a little bit easier, I'm only making you implement this, this heap invariant right here, that all children values must be greater than their parents. So how do we do that? Let's open up the test cases next, tab E tests/test underscore heap.py. And we have a bunch of test cases here at the top checking whether the heap invariant is being satisfied or not. And so I want to run those test cases and just check to see whether they are passing or not. We'll start by doing our PyTest here. Let's make sure that's out of the way. PyTest on test underscore heap. So it's only on the heaps here. And now we can see that we got a couple of these heap satisfied that are failing down here. Okay, so let's think about how to actually implement this. Well, the standard pattern that we have, again, is that we have our method right here, our ordinary method that is not a static method, that is sort of our clean interface, the thing that we expect users to be using right here, and it just calls this underscore version of the function, which for us is this static method down here. And now on our static method down here, we have to implement it. And so let's remind ourselves what this heap invariant says. It says that all children values must be greater than their parents. So let's go ahead and say that if node dot value is greater than node dot left, let's see, node dot left dot value, then this is one of the conditions that we need that passes. And if node dot value is less than node dot right dot value. So those are the two things that we need to hold in order for the heap to be satisfied. In this case, though, we can't just directly do node.left and node.right because we don't know that there's going to be a left and a right child. So I'm going to use my pattern of here. We'll start by assuming that the heap invariant is satisfied. And then at the end, so it will return red like this. And then we're going to try to find all the falsifying cases. So if we have a left child, if node dot left, so if left child is not equal to none, then we need node dot value less than node dot left dot value. This is our thing that we need to be satisfied here. So we'll say ret and equals that. This is less than that. That looks good to me so far. And then similarly, we need to recurse down onto this left child and make sure that it's satisfied for the left child. So ret and equals heap dot underscore is heap satisfied like this on node dot left. I think that looks good to me. And so now I'll do some fancy Vim work, and I know that the check for the right is going to be the same as the check for the left. So I'm going to just copy this section of code. I'll press Shift V to enter visual line mode down here, so I can select multiple lines at a time. Lowercase v enters what's called visual mode, where you select individual characters at a time. Shift V, uppercase V, selects individual lines at a time. And I want to yank these three lines with the Y key, and then come down here, press P to paste them. In order to change this so that it's now uh, basically, yeah, in order to check the right side of the tree, I'll need to replace all these lefts with a right. So I'll select what I just pasted, press colon here, and you can see that here it's automatically added this sort of weird looking incantation right here. This means that whatever command I type into the command mode right now is only going to apply to the visual selection right here. If I wanted it to apply to everything, I could delete that, but I do in fact want it to apply only to that selection, so I'll leave that there. And then the command to replace is s slash the thing that you're looking for slash the thing that you want to replace it with. So we'll replace the left with the word right, like that. And in this case, I think there's only one per line. By default, this expression right here only changes the first instance of this to this on each individual line. If we want to make it apply to every instance on the line, which is usually what I want to do, you have to add the /g at the end. The G over here stands for global. This is called a replacement regular expression from, it's inspired by the program SED, S-E-D, a very popular command line tool. And people will be using, programmers use this sort of syntax all the time, all over the place to do find and replace. So I'll hit enter right there. Now we have all those lefts got replaced by rights like that. Escape :W. I'm not sure if this is correct or not. High possibility for bugs, but let's go ahead and test it. On the right-hand side, up arrow, rerun this, and now we still have some is heap satisfied being falses. So let's dig into that and take a look at what's going on. This is the test case 1 that we are looking at. So over here, let's head over to test case 1 and see what's going wrong. I'm going to start by just drawing this tree out and making sure that I know whether it should pass or not pass here. Well, yeah, so here actually it says that it should pass. So let's take a look at what this tree looks like. I'm going to, there it is. So we have, okay, 0, left, 2, 2, 0, left, 2 here, 2 here. And then the left, right is 5, right is 0. So left, right is 5, right was 0. And then right, left is 0, right is 30, right, left, another 0, right, being 30, like that. And now it's wants to know, is the heap satisfied? This up here is saying that it should get me true. That's what this assert statement right here is saying, that this heap should satisfy the heap condition. But over here, I am asserting false. Okay, so let's think about why that's the case. I think it's because on my heap over here, I have the 0 that's been inserted multiple times. And so being careful about this edge case, it's totally fine to have repeated elements like this. I just have to handle that down here and say that it's okay if things are less than or equal to, instead of just strictly less than. And come down over here, rerun that, and okay, that passed the that satisfied 1 test case, but now we have this satisfied 3 test case. So let's take a look at that one next. Another edge case over here is heap satisfied 3 with the empty heap. This should be satisfied, but I'm saying it's not satisfied. And so let's see if self.root heap is Otherwise, return true. So let's remind myself what this test case says. Is heap satisfied 3? Heap equals heap. Heap dot is satisfied. That should be true. Is it? And then here it's saying that it's failing that. So let's take a look at the actual test case again on how to find this. And I forget how to do the filtering. My heap object has no attribute to list right here. Uh, yeah, so ideally I'd be running just this one test case at once. I forget how to do that. So rather than, I should look it up, but I'm just scrolled a little bit here to get to this. So self attribute error, heap has no attribute to list. And so now I have to think, why is it calling this to list function? Inside of here, it's there's no to list anywhere. But if we remember from our previous functions, our previous constructors, we were calling toList internal to the constructor. And so I think that's what's going on right here, is that our constructor right here is calling a toList function, which doesn't exist. So let's take a look at that constructor and see if that is correct. I'm just doing a search for heap. GG, take me to the top, and take next. Here in it, so it's not calling, I don't see any call to a constructor right there. It is heap satisfied. Oh, so I'm reading my test cases wrong here. This is heap satisfied is where is what that's happening. Maybe no. Is heap satisfied? Is heap satisfied? Self equals attribute error raised in the repr function. So in the repr function right here, that's where self dot to list right here. So we're calling the to list function inside the repr function when we are printing out this heap. Why are you calling the repr function? I don't know. Well, this is easy enough to fix. I will go ahead and implement the toList function. Oh yeah, we don't have a toList function. Yes. Duh, Michael. Duh, Mike. The so this toList function, we don't have it in this heap class. But we should be inheriting this toList function from the binary tree class. And if I research for the word heap here, or let's just come up to my class definition, I press the square bracket twice to take me to the top up here, top level definition. And here in this heap right here, it says that heap is currently not a subclass of binary tree. I'm gonna just really quickly open up the binary tree. Inside of binary tree, this is where we should be getting the toList functions right here, but we were not. Inside of the heap class, we have no toList function. We're inheriting that, or we should be inheriting that from binary tree like that. Save that, come down over here, and now rerun those test cases. And oh, still getting the is heap satisfied 3 right here problem. Okay, let's go ahead, and I need to remind myself PyTest filter test cases by regular expression. What's the command line flag to do this? Yeah, so all of these things about like cool command line flags, -K it looks like, are things that are very useful, but nobody remembers these things. Way too many things to remember. That's why we have Google. That's why we have ChatGPT to help us out. So -K is heap satisfied. There we go. So now we're only working on just this one function at a time. Heap object has no attribute root if self.root. So my heap constructor right here heap object has no attribute root, right here. And it's because my, well, let's see, let me just restate that again. In this line right here, under is heap satisfied, the self instance does not have this attribute root over here because I've never created that attribute. And the heap constructor is what's supposed to be creating that attribute for me. Up here, we can just do self.root equals none, like that. And now that will create this attribute. It'll still be empty. So hopefully that should pass this check now. And this is not a correct implementation of the constructor. This is only the case for when XS already is none. You'll still have to handle the case when XS contains something in it and make sure to insert those. So let's save that now. Up arrow, rerun this, and now we're passing all 6 of those test cases. That's great. Yeah, so big picture takeaways so far. We have our is heap satisfied correctly implemented? This is always the thing that you start with when you're implementing a data structure, is implementing these check debugging functions that will help you verify that your other functions are correct. But whether one of these functions is correct or not does not just depend on the code inside the function. That we pretty much had this function, I think we actually did have this function 100% correct when we first wrote it out, but we were still failing a lot of other test cases because of errors elsewhere in the code. And figuring out exactly where those errors are is a tricky process, and we really have to understand a lot of things about the code in order to do that. The first time we had this toList function, the error was happening in our repr call up here due to the toList function not being implemented yet. And in order to realize that or in order to get a fix to this, I had to realize that, hey, we already have this function implemented somewhere else in the binary tree class. Maybe I didn't inherit correctly. And in fact, I didn't inherit. I didn't have any inheritance going on. So adding the binary tree right here gave me access to that toList function, fixed the repr function, which fixed the test case for is heap satisfied. That still didn't fix everything though, because we were still failing a test case relating to the root attribute not existing yet. And the root attribute was supposed to exist inside of this init function. The init function is what was supposed to create it. Again, the error did not show any errors related to the init function or the constructor right here. I had to intuit that, figure that out based on the error messages that we were getting later on, that this attribute didn't exist. And if an attribute doesn't exist, it means that, or the normal place of creating attributes is inside the constructor. So if you're getting attributes not existing, then the constructor is a good place to look for errors. Okay, so that's the is heap satisfied function, and now we're ready to start on our insert function sort of in earnest here. In order to find functions, one of the things that I commonly do when I'm searching, instead of just searching for the name of the function, put an opening parenthesis at the end of that, and that lets me jump to where the function definition is and not like somewhere in the comments or anything. Okay, so fix me, implement this function. We have a hint at least, so the pseudocode will find the next position in the tree using the binary representation of the number of nodes. So this is what this is basically the same pseudocode that we talked about in our sort of written explanation earlier. Here, if you want more explanation about the how that binary system works for why it means go left and go right, this Stack Overflow link is a good reference for that. But yeah, let's go ahead and get started on this problem here. So the first thing I'm going to do is let's just take a look at the test cases and see if there are any test cases that seem like really helpful for us. So there's a handful of test cases mentioning insert. The remove ones here, okay, so we have to get the insert totally working before we work on remove. That makes sense. Oh, and then we have some test cases combining remove and insert together. Those seem like they'll be fun to get working. But these are probably be the test cases that I can immediately pass right here, just related to insert and then eventually insert list. Let's come back up here, and so let's add our dash k onto heap underscore in. Oh, that's not going to match anything. Insert, like, it's still not going to match anything. Insert, there we go. So this is matching the insert and the insert list functions. Let's see if I can do a fancy regex here. I think it'll work. The dollar sign indicates the end of a line. Nope, it's not working. Okay, never mind. So yeah, because the heap insert list contains the heap insert, it's matching both of these two test cases right here. But we're really focusing on the insert function right now. Let's come back over here and well, let's see. So the insert function, this seems like it's going to be really complicated to me. And so this test case over here does not seem like something that I want to just directly start with. And so what I'm going to do is let's do some interactive Python. I'm doing my Control R, looking for my Python path command from before. I don't see it anywhere. So let's Python path equals dot. We'll see if I can type it out from memory. Python 3 containers slash heap.py. Whoops, and we need to add the dash I right here to go in interactive mode. There we go. And I have access to the heaps. Yes, excellent. Okay, and what I'm just going to start, I'm going to use this to manually call the insert function up here. The first thing, so this first test case, or this first piece of the pseudocode right here, I need a binary representation of the total number of nodes. Okay, so this means that I also need access somehow to the total number of nodes. So we've got a note here. You'll have to explicitly store the size of your heap in a variable rather than compute it in order to maintain the O of log in runtime. Okay, so let's do self dot number nodes plus equals 1, like that. And this is going to, if I try to just, we'll do h equals that, h dot insert 5. We're getting this error. Heap has no attribute number of nodes like this. So let's come up to back to the constructor and add this attribute. I'm going to do im_a right here to create a mark so that I'll be able to come back to this really easily. Then I'll do square bracket to jump up here, and then down here in the constructor. And let's do self.num nodes equals 0, starting off with no nodes in the tree. Quotation mark A to get back to where I was at. Save this now, Control D, up arrow, and rerun this. And there we go, no error messages. Okay, so this is getting a little bit better. Well, I mean, it's progress a little bit, I guess. I really want to make my test cases over here, or my get really fast feedback on the things that I'm working on. And this right now, I have, in order to call this insert function, I have to run 2 separate lines. I don't like that. That's slowing me down. So I'm going to combine this all onto a single line like this. And so what this is going to do, the semicolon just separates lines in Python. It's like a new line character. It says first create the heap, then insert it, then display it. And so I'll be able to get a little bit faster turnaround time on how things are working here. Press Control T to end that up arrow, and there we go. So now we have a fast evaluation loop of what's going on. Okay, so now we'll have a representation on the number of nodes here. What we need is a binary version of that representation. So I could think about how can I manually convert things into binary, or I could just use Google and say Python convert number to binary. And what are you going to tell me? Use the bin function to convert from a decimal value to binary. Let's see how that works. Bin 10. Okay, so this is what that looks like in binary right here. And so let's call our binary str bin of self.num nodes like this. And here that gives me this whole string. This 0b up in front, the 0 means that this is a number, the b means it's represented in binary, and here's the actual binary representation. The very first number here is again always going to be 1. So I want to strip out these first 3 values right here. I want to strip out these things and only keep these 3 things over there. I can do that with binary, oops, we'll use there we go, a little bit of slice magic like that. And now to see how this is working, let's print it out. I'll undo again. Anytime I'm debugging these things, I do the variable that I want to debug and then at p like this. That at p is that macro that we defined in a lab a long time ago. Gives me very fast ability to print things out, and then I know exactly what I'm printing because of I'm telling myself there. Oh dear, so the binary string is empty, so that seems like that did not work at all. What's going on here? So that string, if we did that 3 colon, that would work. So bin self dot no, it's binary string, binary string. Binary string. Let's self dot num nodes. What is that equal to? Notice that I'm just trying to go, yes, go through here, get fast iterations on everything. Every time I'm changing code, I'm adding more print statements and then just immediately seeing exactly what they do. And I'm not trying to write a lot of code at once between my print statement evaluations, between what I'm doing over here. I make very, very small changes to the code and then check to make sure, is it doing exactly what I'm expecting it to do before I make big changes to the code. And so here, yeah, I've had an aha moment on that when I was using my bin function up here, which is my bin function, I was using the number 10 instead of the number 1. Let's do bin of 1 like this. And it has just the numbers 0, b, and 1 like that. And so when I did the slice like that, I get the empty string. And so that's why when I'm printing binary string right here, there's nothing printed because it's the empty string. I can make that a little bit more obvious for myself in the future by, say, putting square brackets around like this, and then whatever the binary string is right here will be inside the square brackets, and so I can see the end and the start of those square brackets. There we go, so there's nothing inside there. Okay. Okay, so yeah, if there's and if there's nothing in the in the tree, nothing in the nothing in the heap yet, then it makes sense we don't have anything in our directions left and right to go because there's no children at all. So we can have an if statement of something like if self.root is none. There's a lot of ways that I could do this equivalently by like checking the num nodes or things like that. But I'll just check self.root is none, then self.root equals node with my value that I'm trying to insert. And I don't remember what we called that. I'll press Control Y to scroll up my screen right here without moving the cursor. Control E goes down, Control Y goes up. These are, so Control Y is short for, the Y is short for your. So this is some old English coming into our Vim here, and Control E, short for after, more old English here. The B and the A for like normal English was already taken, and so we decided to get some history here, making this E and Y, and that should be a lowercase y. Sorry, Control lowercase y takes you up, Control lowercase e takes you down. Your after. Self.root equals node, and then yeah, value is the thing that we're putting in there like that. So Control D, up arrow. Let's come back to this here, and we still have heap is none down here. Yeah. H dot value somehow h dot root dot values 5 h. There we go. If we do string of h dot root, there we go. If we do string of h, does that work? There we go. Yeah. So somehow my binary tree implementation is messed up from something. I think I didn't actually use the solutions branch as my base branch here, so I'm not getting access to things like a to list function to actually print things. It's still just returning none right here. So instead, I'll be using the str function to visualize my tree like this. And so I want to replace my one line function up there with a strh like that. And so we're getting the final line out here is my representation of the tree. Okay, so this looks good to me so far. And it works for implementing one thing. What if we implement two things? H dot insert. I want to start with the simple case of where we are using a number like 6 that is bigger than the number than the root, because then we don't have to do any of the trickling. All we have to do is find the right location to insert. So I'll try this, and we can see here that our, our tree is not being updated yet. The 5 right here has not been updated with the 6, and that makes sense because there's no code over here that does the actual update. But now in my binary string representation, the very first time I call it right here, I am binary string is nothing. That's great. The second time I call it here, we have a 0 inside of it. So it means that we should be going to the left somehow. And now we have to think about adding some sort of recursive function that's going to do this for us. I think in the past, well, yeah, let's go ahead and add a static method at static method def underscore insert. And then the node that we're inserting, the value that we're inserting. In this case, we're also going to need access to this binary underscore string variable as well, I think. And down here, let's do an else. Heap dot underscore insert of self dot root comma value comma binary string like that. And down here, let's just print underscore insert. So I know that I'm going into this function. And let's tell myself what the value is that we're printing here. And let's tell myself what the binary string is as well. So notice that I'm not even like trying to work on this function at all yet. I'm just trying to get my debug stuff set up because I know that I'm going to need my debug stuff. Okay, we'll change this to use the f strings node value binary string. There we go. Okay, so here when I call in the insert function, the node right here, I'm just printing out node because I know that this could be potentially long and complicated. So I'm just putting a placeholder right here. The important thing though is that I'm inserting a 6 and then a 0 right here on my binary string. And actually, well, let's go ahead and do this. We'll do node equals node value equals and binary string equals. Yeah, some of the most productive things you can do as programmers is just getting your print statements, your debugging stuff set up properly. So I often spend a lot of time just making sure that this stuff looks pretty and looks like it's going to make me happy, and I'll have fun working on it as I'm coding. So there we go. I like what that looks like. It's giving me lots of good information now. And so now what do I have to do? I have to look at the the top value of this binary string right here. So if binary string of 0 equals 0, we said 0 means go left. Then, so we'll be doing something with the left node of the, oh, sorry. We'll be doing something with the left child of the node over here. Node dot left will be equal to something. And in this case, we want it to be node value like that. Go ahead and add if binary string of 0 equals 1, then node dot right equals node value. I'm a little bit suspicious of myself right now. That I'm doing a lot of work here at once. I'm writing 4 whole lines. Honestly, I'm a little bit scared right now, and you should be too when you're writing this much code at once without testing. I'm adding this line right here because it's exactly this value 6 that I'm trying to insert that I'm testing on right now. And so let's, but I'm also pretty sure that this is going to be the very next thing, the very next case that I'll need to handle right here. So we'll going on to the right after that. So I'm getting ahead of myself, but we'll try both of those two things at once. So added the 6 right here. We can see that here's the resulting thing, added the 6. That looks good to me. So now I'm going to do an h dot insert of 7 like so. And now you can see that my output here is starting to get a little bit long, a little bit, I don't know, ugly, hard to follow along what's going on. So before I even look at that output, I'm just going to add some more print statements up here to make things look a little bit nicer. Really, the reason this is hard to read right now is there's just so much stuff and it's not organized well. So let's up arrow, rerun this. Now that I've added this print statement, we'll add new lines between each of my calls to the insert function. So here I can see everything that's going on with inserting the value of 6. And then here I can see everything that's going on with the inserting the value of 7. And um, uh, uh, yeah. Um, so we insert the value of 7 right here. This is going on to the right-hand side and inserting that right there because the binary string is equal to just 1. It's a little bit confused, like why is this binary string equal to 1 being printed up here above the insert? It's because I'm printing the binary string up here in the non-underscore insert function. So I think actually it probably makes more sense to move the blank line up there. Let's add a print insert like this, value equals value that, and now we're running that. There we go. This looks a little bit nicer to me now. So here's the insert 5 stuff. Here's the insert 6 stuff. Here's the insert 7 stuff. And then inside of insert 7, you can see that it calls the underscore insert right here, which does this right here. It's also, so here, let's add a little bit more debugging information here. Notice that like I have very few, I have little confidence in my abilities to keep things inside of my head, but I have a lot of confidence in the computer to help me understand things. And so I don't wait till I have bugs in my program to try to insert debugging information. I insert this debugging information as I'm going all over the place. And I spend a lot more time thinking about inserting this debugging information than I have actually the problem itself. I just want to make sure I'm understanding exactly what is going on in my code. And so here, these zeros and these ones correspond to these print statements right here, telling me which of these if conditions I'm actually going into. So the 0 and the 1, and that's what we wanted. For the value 6, we're going on to the left, and then for the value of 7, we're going on to the right. Okay, that's great. So now I think I'm ready to try to do insert 8 like this, and we'll see what happens. And so here, when I did the insert 8, we can see that the this is the node that got passed in 5, 6, 7 right here. And we overwrote that 6 with the 8 value right here. So here, it's not just enough to check whether the binary string is equal to 0. We also have to make sure that it's the last thing in the string if we're actually going to do the writing. So here, if length of binary string equals 1, then we'll do this. And I'll go ahead and add that down here. If length of binary string equals 1, then I will do that. Up here, we run. Notice that I didn't try to get the 8 actually inserted yet. I just wanted to make sure I'm not overwriting the 6 before I try to insert the 8. Okay, that's good. So if it's not equal to 1, then I'm in the case of the 8 over here. And so now we would do something like my recursive operation. Node dot left. Actually, I think we can do it just heap dot underscore insert of node dot left. So here's the getting the problem smaller part, going onto the left side, still inserting the same value, but now my binary string, we want to take off the very first position over here that I've already looked at. Gabe, I'm not going to try to do the other branch at the same time until I've tested this one. And this now looks good to me. It added that there. Okay, I'm happy with that. So now that looks good to me. And let's add our insert statement over here. I'm changing that to the right. And I think that should be good. Control D up, rerun this, up arrow, and let's do an H dot insert of 9 like that. The 9 here got inserted sibling to the 8. I like that. Okay, let's keep going. H dot insert 10. Okay, that's over here on the 7. That's good. We're maintaining the completeness. H dot insert 11. Okay, that's good so far. Here's another test though. This tree is totally complete right here. If we had another one, it would go onto a new line. You should make sure that you understand why that's the case. Just reading this output down here, hit the 12, and boom. 12 is the left child of 8. So I've very comfortable with parentheses reading them. I can just visualize this in my head, all of these trees in my head. You should be, if you're not able to do that, which is totally okay, you should be drawing these out and making sure that you're following along about why I'm happy with what this is looking like right here. At this point, let me just take my time right here. At this point now, my command up here is getting a little bit unwieldy to test things with, but I'm happy with how things are going. Let's review our pseudocode and review what we've done before at this point. I've done this first step, finding the position and adding the value into this position, steps 1 and 2 right here. The last thing is this trickling up procedure. That seems like it'll be potentially complicated and something that I'll really want to have good debugging feedback for. So in order to make sure I have that good debugging feedback, I'm actually going to stop working on this problem for a second, and I'm going to change to the insert list function, insert underscore list, like this. And the reason is because this will make it easier to call the insert function over and over again. So for x in excess, yeah, there we go, for x in excess, self dot insert x like that. And now I can change this huge long nasty thing. I'm not even gonna heap into h dot insert list, and now 5, 6, 7, 8, 9, 10, 11, 12, like that, string of h. And now it's much easier for me to create new test cases. This is all still doing the same thing as it was before though, so that's great. Okay, back to underscore insert. Okay, the last thing that we have to do is trickling up. So let's start now. So this was my first test case, inserting 5 and 6. That did not need to trickle up. Now let's check something that does need to trickle up, the 6 and the 5. We need to end up swapping the 6 and the 5. How are we going to do that? Okay, so where in the code will I do that? Well, it seems like right after I insert, this is the spot to check. So if, let's see, node node dot value. Am I printing out the node dot value anywhere? Okay, so I'm drawing. It's not immediately obvious to me what the next procedure, what the next exact thing to do is here. So I'm just going to start adding print statements because that helps me just making sure I'm thinking about things right, or it gets my mind in the right mode for thinking. Okay, so this value equals never got printed anywhere down here. So that can't be can't be the right spot to think about trickling. So let's change the indentation like that up there. Print. Okay, so the value is getting printed right here at a spot where I need to do the trickling. So that seems like now a good potential spot to think about doing the trickling. We have the node dot left equals the node dot value. So we have access to our current node, and we have access to the child node, to node dot left. So let's think about if node dot value is greater than node dot left dot value. If that's the case, then we should swap them. Then node dot value comma node dot left dot value equals node dot left dot value comma node dot value. This in Python is syntax for swapping two variables without creating an intermediate variable. And I'm going to delete that, but I will print a swap right here. So we did print swap, and it did do the swap 5 and 6. Ooh, that looks good. Okay, and let's copy that down here. That seems like it worked for this small test case. So let's just try going on to the other side. Let's change out all the lefts with right using my sed syntax again, like that. Save that over here. Control D, up arrow, rerun. And 6, 5, 4. Ooh, okay, so 4's at the top, 6 and 5 down below. That looks nice. What happens if I insert a 3? Well, first, before I try inserting a 3, let's try inserting an 8. The 8 gets inserted in the right spot. If I insert a 3, that 3 should trickle up all the way to the top. Instead of going straight to inserting it a 3, though, I'm just going to insert a 5 here and make sure that the 5 I insert here and the 6 I insert there will swap. And they did. So 6 here, 5 here. Now let's go for the 3, and it swapped. Ooh, everything's looking nice at this point. So I think we might have a solution here. I'm not sure yet. So I'll just try to do the PyTests now. And again, the PyTests, you'll notice that I've not used it at all during my debugging processes. I've only used it in the evaluation to check if I'm correct or not. And here we can see that it is not correct. It found a falsifying example at just the list containing 0. Uh-oh. Type error. Oh, dang it, the toList function. None-type is not iterable. Binary tree toList. I don't have that implemented. Let me just try really quickly. Branch, get checkout, BST, solution, merge, BST, solution, already up to date, dang it. So let's see, get, okay, yeah, so let's make sure we're on the same page about what I'm doing right here. The reason this test case is failing right here is because this toList function is not available. toList function is not available because in my binary tree.py right here, toList is not available. It doesn't exist. So we have to get access to this function somehow. And I'm just going to use my Git skills to do that. Yeah, we'll do it over here. Let's get status. Let's add containers. Heap git commit -m. Maybe insert is working, question mark. And now, so get remote dash v. I do have an origin right here is that, so I will do a get pull origin vst underscore solution into the heap branch, already up to date. That's I have yeah, I know what the problem is on Git side, why it's not there, but it's not a simple explanation. So is there a simple way to check this real quick? Git checkout origin slash vst solution, then containers slash binary tree.py, edit that slash to list function. There we go. Here's the implementation. I'm going to copy and paste this over into, actually, I'll do it even fancier. Copy containers binary tree.py into temp.py right here. Git checkout heap, copy my temp.py to container slash binary tree.py. And now over here, press :E, that'll reload this file. And there we go. We have all the contents now. We have the toList function. Excellent. We'll be able to solve this problem now. And PyTest. And it does pass. Yes, excellent. So yeah, I don't know, the Git stuff that I did there's not necessarily super important about what was going on, but I'll do a quick high-level recap in case you missed that. The problem was that my binary tree.py file did not have the solutions inside of it because of yeah, it didn't have the solutions inside of it. And so what I did was I just got the solutions file and copied it over to where this binary tree.py file was. So now it has the solutions. And in particular, it has this toList function right here, which was where the, if I scroll up, that's where our previous code was failing at. The insert function was failing because the assert right here was checking to make sure that the X is inside of the list that corresponds to the heap. And this function wasn't implemented. So by getting a working binary tree file into my repo, this function was now implemented and it was passing the test cases. So that's everything for, this is a working version of the binary tree, or sorry, of the insert function here for the heap. It's nice to not leave all these print statements in here that still pass in the test cases, but we don't need them anymore. And they will not only clutter things up, but well, yeah, we'll just be cluttering things up for future files, future tests that we're running. So I like to, instead of just deleting these print statements, I like to comment them out so that if I need to get back to them later, I have them available here. But they're not there if I don't need them. So there we go, passing those test cases. There's a handful of other like things that you'll have to implement, like this find smallest function. Should be straightforward to do that. The remove min function here, though, that will be the tricky one to do. Again, don't just dive into it like trying to do all of these steps all at once. Really go step by step, making all of like getting a nice debugging output as you're going. Strongly recommend you do that. You can see that like as I was working, I spent a lot more time focusing on just making my debug print statements here nice and pretty so that I could visualize what was going on. And that made it basically obvious for me what lines of code to work on. Also, like if you're writing more than 1 or 2 lines of code in between doing your tests, then you're writing way too much code. You should be like everything you do, make sure it works before you do something else. Having this methodical procedure will let you implement these functions very quickly. This took me about an hour or so because I was walking through explaining everything as I was doing it. If I hadn't been talking, this probably would have been like a 10 to 15 minute thing for me. And it's because I was going slow that I was able to go so fast. Slow is fast in the coding world. Um, yeah, good luck.